Today's lesson will focus on compositions of functions. We have some basic operations that you are probably familiar with, and then we have some composite functions down here, f composed of g of x and g composed of f of x. And what these mean, just to refresh your memory, is that in this first example we have f composed of g of x. So meaning we take g of x and we plug it in for x in our f function. In the second example, we would take our f function and plug it in for x in our g function. We'll be focusing in this area for most of this video. But first, let's go ahead and review just the basic operations. Here's two different ways to write each of these. We have f plus g of x, which can be written this way, f of x plus g of x. Same thing for subtraction, multiplication, and division. Remember with division, that's special. We have a domain restriction because our denominator can never equal 0, or we have division by 0 in an undefined function. Let's go ahead and try some basic examples to start with. So here we are given two functions, f and g, and we want to evaluate. So we want to add them together in the first example, subtract them, multiply, and divide them. So go ahead and pause the video and try this yourself. See if you can remember how to do that. In these second two examples, go ahead and find the domain as well. In our first example, it's as simple as just taking this function and adding this function. Now all we need to do is combine our like terms. So we have 1x squared plus 5x plus 1, and that's our solution. In our second example with subtraction, did you remember to put the second function in parentheses? We are subtracting the entire function here from our f function. If we don't put it in parentheses, we will only be subtracting the 3x. In order to finish solving this, then we would need to distribute the subtraction into the parentheses. Distributing that negative gives us a negative 3x and a positive 1. Be very careful to watch that detail. Combining like terms, we end up with x squared minus x and then plus 3. And that is our final answer for subtraction. Let's go ahead and move on to the bottom two. For the first one, we're just multiplying the two functions together. We use the distributive property to help us with this. I will take all of the x squareds and multiply it by each of these terms. I will take all of the 2x and multiply it also by each of those terms, as well as the 2 and multiply it through. Remember, with multiplication, order doesn't matter. So I could have put 3x minus 1 first. Once I've multiplied each of these terms into this second binomial, I have this long polynomial here that I need to just simplify by combining like terms. When I combine like terms, here's what I end up with. And this is my final answer for multiplication. But now we need to examine the domain. So the domain, remember, is all the x values that will give us a output, that will give us a y value. Well, in this function, we always want to look at our final answer here, unless we are composing more than one or we have a fraction such as this. In this case, this is just a cubic function. We don't have any domain restrictions. We can plug anything into this and we will get an output. So our domain for this first one is negative infinity to positive infinity. No domain restrictions. Let's go ahead and examine the second one. For the second one, we just take our f function and put it over our g function. Normally, I would look at the numerator and see if I could factor it, but in this case, this cannot be factored evenly, so we'll just leave it as is. Looking at our domain, I'm looking at my denominator, and I'm trying to figure out what would make this equal 0. An easy way to do that, remember, is just set it equal to 0 and solve. If we do that, x is equal to 1/3, so then we know that all values will work with the exception of 1/3. So I will go from negative infinity to 1/3, then the other side of 1/3, all the way to positive infinity. And those are our very basic functions. Now let's focus on our composition of functions. functions that are composed of one another. In these first two examples, we have f composed of g, which is composed of 4. In other words, we're going to evaluate g of 4, take that value, and plug it into f. If I were to write this out, it would look like this. Always start from the inside and work your way out. So the first thing we're going to do is take our g function and evaluate it for 4. We'll take 3 times 4 minus 1. 12 minus 1 is just 11. So now we can write this function this way. F, we're going to evaluate at 11. This inner portion, g of 4, gave us a value or an output of 11. So now we're going to take our f function and evaluate it for 11. So we would have 11 squared plus 2 times 11 plus 2. And that will get us 121 minus 22 plus 2 for a final value of 101. So when we take f composed of g of 4, we end up with a value of 101. Try this second one on your own. Pause the video and come back and compare your answer. All right, remember that this is going to look like this. G composed of f of negative 2. In other words, let's go ahead and evaluate our f function first for this negative 2. Remember, work from the inside out. So we are going to have negative 2 squared plus 2 times negative 2 plus 2. This leaves us with 4 minus 4 plus 2. The 4's cancel out and we are left with 2. In this bottom function now we have g of 2. So we are now going to evaluate our g function for the value of 2. F of negative 2 gave us an output of 2. So to do that, we're going to take 2 and plug it into our g function. 3 times 2 minus 1 is 5, and that gives us our final answer there. Now let's look at what happens if we compose one function with another. In this bottom situation, we have f composed of g of x. All this means is we're going to take our g function and we're going to put it in the f function everywhere that we see an x value. So it would look like this. Instead of x squared, we would have 3x minus 1 squared. And then instead of plus 2 times x, we would have plus 2 times 3x minus 1, and then plus 2. It's that simple. All we need to do now is simplify. Simplifying this, 3x minus 1 times 3x minus 1, we end up with first term squared, first times second times 2, and last term squared. Remember, that's a shortcut you can use rather than taking 3x minus 1 times 3x minus 1. Distributing the 2, and then add 2 on the end. If we combine like terms, we end up with 9x squared. Our negative 6 and positive 6 cancel. 1 minus 2 is negative 1, plus 2 is 1. All right, let's think about our domain for this one. Do we have any restrictions? And right now you should be saying no, and you would be correct. When we are composing functions, we always look at the domain from our inside function first. So if I look at 3x minus 1, that's a linear function. There are no domain restrictions. Then I look at my composed function, the entire thing, and that's a squared function. Again, no domain restrictions there. So our domain is negative infinity to positive infinity. Let's look at a little bit more difficult example. Here we have some fractions, so we know we're going to have some domain restrictions with this. But let's go ahead and compose them first. We have f composed of g of x. So we have our f function, and instead of our x, we're going to put in our g function. We don't want to leave it like this because we never want to leave a fraction divided by a fraction, so we need to simplify. In order to combine a fraction with a number, we need common denominators. Our common denominator here will be x, so we need to multiply 3 by x over x in order to have a common denominator. When we do that, we get 3x over x, and now we can combine these two together to get negative 2 plus 3x all over x. Well, this is a little better, but we still have a fraction divided by a fraction. So remember, when we have that, division is the same thing as multiplication by the reciprocal. So we can flip our denominator to be x divided by negative 2 plus 3x. And 1 times anything is just what we have, anything. So that will equal x over negative 2 plus 3x. And that is the solution to f composed of g of x. But what about our domain? Well, remember with our domain, we always look at our inside function first. So we look at g of x. In this case, it's simple. X cannot be 0. So 0 will not work. Then we look at our final function, our total composed function. Here, we could take negative 2 plus 3x to see what makes it equal 0. And when we do that, we can see that 2/3 causes this denominator to equal 0. So our domain will start with negative infinity. We'll go all the way to 0. Remember, we can't have 0. Then on the other side of 0, we'll go all the way to 2/3. And then on the other side of 2/3, we'll continue on to infinity. This is our domain for this second function. As we begin to wrap up this lesson, let's look at compositions of functions backwards. So say we have a composed function, p of g of x is this, and we want to identify p of x and g of x. One thing to remember on these is that there isn't just one right answer. We can solve this in multiple ways. This requires you to think outside the box. There's not an algorithm that will solve this problem for us. We just have to take what we think is the inside and pull it out. Well, something like this, I think of the inside as what's under the radical. So we could start by calling that our g of x, 3x minus 4. Well, in order for it to be under the radical, we need to have a p function that has a radical. So we could just call that radical x. And then we can test it. If we take this and put it into p of x, we should get that. So this is one way to do this, but there are other ways too. If you want to challenge yourself, pause the video and think of another combination of functions that could create this composed function. All right, well, let's think about it. What if g of x was something else? What if it was just 3x? Well, then what would p of x have to be in order for this to work? Well, we know there has to be a radical, and we know there has to be the minus 4. So what if we had x minus 4? That would work, because we would plug in the 3x in place of the x, and we would still end up with the same function. So remember, if you want to challenge yourself, think about how to do this in multiple ways. Let's look at this. What if we want to find the composite function that is equivalent to this bottom function here? So we have 3. Was it f composed of g composed of h? Was it g composed of h of f? What was it? So again, pause the video and challenge yourself. See if you can come up with a composition that equals this. Here's what I came up with. If we take 2x minus 5 and we put it into h, we get 2x minus 5 squared. And then if we put that into g, we get 2x minus 5 squared plus 2, which is equivalent to this. So where would you use these compositions of functions? Well, you might use it in a situation like this. We have a demand equation here where the price P of a certain product and the quantity X sold follow this demand equation. And then we might have a cost equation. The cost C of producing X units is modeled by this equation, but maybe we want to combine these in order to find the cost as a function of the price. So depending upon the price we charge, the cost may change. That's an example of a real-world problem. You're going to be trying some of these in your practice. And that concludes our lesson today on compositions of functions. So hopefully these first four are very familiar to you, and the compositions of functions will be what you'll focus on.